If you lived on Mount Rainier, the 4,394-meter mountain in Washington, you would age faster than a person living in New York City. Time would pass faster for you. But what is time? Time is defined as the indefinite continued process of existence and events in the past, present, and future regarded as a whole. Time can be classified into three elements: the past, the present, and the future. And in our lives, time always appears to move forwards towards the future, but that is merely an illusion. More on that later. Albert Einstein applied this concept in his theory of relativity. Einstein was a German-born physicist who developed the theory of special and general relativity and also won the Nobel Prize for Physics in 1921. He published his paper about special relativity in 1905, but there was a crucial flaw in his own theory. It failed to mention gravitation and acceleration. For the next 10 years, he would try to formulate a new theory in terms of curvature of spacetime. In November 1915, he finally completed the theory of general relativity. The entire theory of relativity is currently our best explanation of the universe and the most iconic, but it is still far from being complete. Other notable theories such as quantum mechanics compete with general relativity, but they are not as provable and applicable. These popular theories collide against each other and are compatible together. The theory of everything, which would explain all the phenomena in the universe, hasn't been created yet. Einstein's theory of special relativity was an explanation of how space works, and it explained that time always passed at the same rate and was absolute, so space itself was a fixed entity. To any observer, particle, wave, or quantum anywhere in space, they should experience time and space exactly the same as one another. It also postulated that the speed of light is always constant in space. The theory of special relativity was not complete, as it was only applicable and proven to work in flat spacetime, which includes all phenomena without gravitational influence. In real space, gravity is very significant and abundant, but special relativity forgot to include this factor. Einstein's theory of general relativity describes phenomena with gravitational significance and is more relevant in most scenarios in space. It describes the geometry and curvature of the universe and models space and time together in a fused continuum called spacetime, which is known as the fabric of space. To better understand the theory of relativity, you need to understand what time actually is and how it works in space. Understanding the concept of spacetime is beneficial for a better understanding of time in space and in the universe. While special relativity deals with flat spacetime, general relativity deals with four-dimensional spacetime. The definition of spacetime listed in the Oxford Dictionary is the concepts of time and three-dimensional space regarded as fused in a four-dimensional continuum. The world we live in is three-dimensional, and our brains don't understand how to comprehend higher dimensions. As spacetime is regarded as four-dimensional, we also cannot correctly visualize spacetime either. Humans simply cannot see or think in four dimensions because we've been designed to only view the world and think in a three-dimensional way. Nonetheless, there are still ways in which we can somewhat visualize four dimensions, and one of these is to use a tesseract. A tesseract is a mathematical four-dimensional analog of a cube. A normal cube has 6 sides of equal length in x, y, z direction, while a tesseract has 24 sides of equal length in the x, y, z, and w direction. We can see a three-dimensional image of a tesseract, but we know that it is not actually three-dimensional. It is a three-dimensional representation of a four-dimensional object portrayed on a two-dimensional medium. Famous astrophysicist Neil deGrasse Tyson explained the fourth dimension in an interview like this.
The tesseract, mathematically, is a higher dimensional object. Well, if you have access to a higher dimension, it means you are no longer bound to where you are in time. Though we can move left and right, and up and down, and forward and back, we have access to X, Y, and Z at will. But you are a prisoner of the present, forever transitioning between the past and the future. In a higher, that's the fourth dimension, X, Y, Z, and time. In a higher dimension, you can step back and look at your entire timeline and access it no differently from how you just walk around in a room. So the question, can you go back in time to change something? That's not even the right question. Once you see your entire timeline, you are always being born. You're always dying. You're always in school. You're always asleep. You're always brushing your teeth. These things are always happening, and you just access them at will.
The concept of spacetime combines space and time into a single four-dimensional continuum, which is the fabric of the universe. Einstein did not draw this conclusion. It was actually Hermann Minkowski who announced it in 1908. Four-dimensional Minkowski space, or flat space in special relativity, is often represented by a two-dimensional light cone diagram, with the horizontal axes representing space and the vertical axes representing time. A light cone is a flash of light from a single event moving through space-time. The walls of the cone represent the evolution of a flash of light passing from the past to the future, or from the lower cone to the upper cone, through the present in the origin point. The region outside the elsewhere section is inaccessible because you would have to travel faster than light to reach it. Light cones describe that the same light that exists in the present, in the now, exists in the future already. Belief in this theory means that history does not seem to happen, but is rather already there and pre-decided. This means that everything we think hasn't happened has actually already happened. This sort of universe is called a block universe, which states that the entire universe is already predetermined and the future and past are encoded into the block universe we live in. If you were outside the universe, outside both space and time, and looked at your life, you would see your birth and death and every other moment in between laid out as different distinct points. From this perspective, time does not seem to flow, but rather is static and fixed. The past, present, and future are all individual points, and our perception of time flowing from the past towards the future is misleading and false. This is why time is an illusion. The ticking of time and our experience of time passing is only because of the fact that we are stuck inside the block universe. Since everything has already happened and is predetermined, is free will even possible? If everything that will happen has already happened, that would mean that free will is also an illusion. Albert Einstein once said, "Time has no independent existence apart from the order of events by which we measure it." Everything that will happen in our lives and everything that we will do is already inherently fixed into the universe. At first, Einstein initially did not accept this interpretation, but later he changed his mind and included it in his upcoming theory. Hermann's interpretation of spacetime proved essential in Einstein's derivation and development of general relativity. This perspective of the universe best suits our current theories of space and time and is the most plausible. Einstein wrote in a letter to the family of his deceased friend, Mikhail Bessel, "People like us, who believe in physics, know that the distinction between past, present, and future is only a stubbornly persistent illusion." We've established that time is an illusion for us, but why does time always appear to go forwards into the future? For us, at no point does time appear to stand still or reverse. The arrow of time always points forwards for us. The laws of physics are time symmetrical, which means that the equations that govern reality do not have a preference for which direction time flows towards. It appears for us that progression can only go in one direction, forwards into the future, which is evident in our lives. This one direction or asymmetry of time is referred to as the arrow of time, and it is what gives us the impression of time passing. The arrow of time is associated with the apparent inevitable flow of time into the future. Many people believe that there is a connection between the arrow of time and a quantity called entropy. Entropy is the measure of how much thermal energy or heat could be turned into useful mechanical work. If you have a lot of energy capable of doing mechanical work, you have a low entropy system, whereas if you have a little energy, you have a high entropy system. This is known as the second law of thermodynamics, and it states that the entropy of a closed system or self-contained system can only increase or stay the same over time, so it can never go down. This means that over time, the entropy of the entire universe must increase, and this is the only law of physics that appears to prefer a certain direction of time. Entropy explains the arrow of time for a number of phenomena, for example why coffee and milk mix but don't unmix, and why a cooked scrambled egg never resolves back into an uncooked egg. In all these cases, an initially lower entropy state with more capable energy for work has moved into a higher entropy state with lower available energy as time has moved forward. There are plenty of examples of this occurring in nature, for example a room filled with molecules, one side full of cold slow moving molecules and the other side of hot fast moving molecules. As time passes, the room will be fully mixed with intermediate energy particles, which represents a significant increase in entropy and an irreversible reaction. One of the ideas involved in the concept of entropy is that nature tends to go from order to disorder in isolated systems. For example, if you tossed bricks off a truck, which outcome would be more probable, disorder or order? Naturally, disorder is a lot more probable, and for these types of isolated or closed systems, the entropy always increases or remains the same. So if you compare the states of different entropy, the one with greater entropy will be later in time. Since you cannot lessen the amount of disorder or entropy applied to a particular system, physicists have reluctantly settled on the second law of thermodynamics as a source of time's arrow. This order always has to increase after something happens, which requires that time moves only in one direction. No matter how we change the entropy of the universe around us, time will continue to pass for all observers at the rate of 1 second per second. The exact correlation and origin between the arrow of time and our perception of time is still unknown, and nobody has the real answer to why tomorrow will arrive in a day and why yesterday is in the past. Entropy is present on small scales that add up to entropy present on significantly larger scales. For example, the entire universe is headed to a cold and empty fate after all the stars burn out, after all black holes decay, and after all galaxies are driven unbound from one another. This thermodynamic state of maximum entropy or thermodynamic equilibrium in the universe is known as the heat death. At the start of the Big Bang, entropy has always increased in the universe and continues to do so through the present day until the maximum state of entropy is achieved in the distant future. This will hinder the processes that cause entropy to increase, since no thermodynamic free energy will be available anymore. This is the reason why time appears to move forwards into the future for us. To elaborate on special relativity, it postulates that the speed of light is constant and is unchangeable in the universe, no matter where you are and how fast you are moving. Even if you are moving at half the speed of light, the speed of light will travel at approximately 2.99 times 10 to the 8th power meters per second. Space and time will literally bend around you for this statement to be true. When moving at these relativistic speeds, time will slow down for you, and the length of objects undergo contraction to keep the speed of light constant. Relativistic speed is a speed that is comparable or close to the speed of light. In the 19th century, it was found that particles' energy and momentum was dependent on where it was in space and how fast it was traveling. The way in which you experience the universe is dependent on your motion through it. Particles that moved close to the speed of light experience time and space differently compared to a particle at rest or moving slowly. Time was dilated. Time moves slower for the particle moving close to the speed of light, and light clocks demonstrate this difference in time or dilation. A light clock is an imaginary clock that consists of a rod with a length of approximately 299,792 kilometers with a mirror at each end of the rod. A signal of light is reflected back and forth between the mirrors, and each arrival of the light signal at the mirror is one tick of the clock. Since light moves at approximately 299,792 kilometers per second, the clock ticks once per second. If a light clock is set to motion close to the speed of light, the clock will be slowed down in the perspective of someone who does not move with the light clock. Imagine a light clock whose motion is perpendicular to the rod. This time the light signal leaves one end of the rod and moves toward the other end, but since the rod is moving rapidly, the light signal must chase after the other end as the rod flees. This results in the light signal requiring more time to reach the other end of the rod. The moving light clock ticks slower than one at rest. This keeps the speed of light constant, which is stated in special relativity. This animation shows two light clocks, one at rest and one moving perpendicular to the rod. You can see the light signal in the moving clock chasing the rod, and to reach the other end, it covers more distance than the resting light clock. As a result, this requires more time. The moving light clock ticks at exactly half the speed of the resting clock. 2 ticks for the resting clock is 1 tick for the moving clock. This is because the light of the moving clock has to cover twice the distance to go from one end to another. To get this precise measurement, the moving clock needs to be traveling at 86.6% of the speed of light. This light clock is a demonstration of time dilation that occurs in the universe, which is described in Einstein's theory of special relativity. Time dilation is a difference in elapsed time measured by two observers due to a velocity difference relative to the observer, i.e. time dilation due to relative velocity. Special relativity states that time can pass at different rates in different reference frames. The time passed depends on the velocity of one reference frame relative to another. A frame of reference is an abstract coded system anywhere in space. The faster you travel through space, the slower you travel through time. Time dilation explains why two working clocks will report different times after different velocities. For example, in the International Space Station, time moves 0.007 seconds slower every 6 months when compared to the Earth due to high velocity. The famous twin paradox is arguably the most famous thought experiment related to the theory of relativity. In this experiment, one of two twins travels at near the speed of light to a star and then returns to Earth. Special relativity suggests that when the twin comes back, he is younger than his identical twin brother. The solution of the paradox lies in the question: why is the traveling brother younger? This question can be solved with special relativity and the velocity difference experienced by the twin in the spaceship using the mathematical Lorentz factor and the special relativity time dilation formula. The solution of the paradox is that the traveling brother is younger since time dilation occurs when something is moving at a velocity close to the speed of light. In the twin paradox, the traveling brother is moving through time slower, but they don't perceive it that way. The perspective of the observer matters when thinking whose time is slower. In the perspective of the twin on Earth, their time is moving normally, but their brother's time is moving slower. In the perspective of the twin in the spaceship, their time is moving normally, but their brother's time is moving faster. Both viewpoints are valid, but once the twin from the spaceship comes back to Earth, he will be younger than his twin. Astronauts from space have aged a little bit less than the rest of us on the Earth, but the effects of special relativity time dilation are only noticeable at very high speeds, close to the speed of light, which means that the time dilation that occurs to astronauts is barely noticeable. In 1971, a popular experiment proving special relativity time dilation was performed. Experimenters from the US Naval Observatory undertook the experiment to test time dilation by having airline flights around the world in both directions carrying 4 cesium beam atomic clocks, which are extremely accurate clocks using electron transition frequency. When the clocks returned and were compared with the clock of the observatory in Washington, D.C., they had gained approximately 0.15 microseconds compared to the ground-based clock. This experiment proved that special relativity time dilation that is caused by the relative velocity of different observers exists. The equation for time dilation between two observers is derived from the Lorentz factor, which describes the factor by which time, length, and relativistic mass change for an object in motion. Relativistic mass in the theory of special relativity is a mass assigned to a body in motion. In the formula, the main reference frame is called one position time or proper time and is labeled by t0. Time between events is called two position time or observer time and is labeled by t. The observer time will always be larger than the proper time since that is the entire effect of time dilation. Both times are measured in seconds. And if the equation is written out, it will be observer time equals proper time over square root of 1 minus velocity squared over speed of light squared, or t equals t0 over square root of 1 minus v squared over c squared. This is an example of a problem solved using this equation. Tanya boards a spaceship and flies past Earth at 0.8 times the speed of light. Her twin sister Tara stays on Earth. At the instant Tanya's ship passes Earth, they both start timers. Tanya watches her timer, and after she sees 60 seconds has passed, she stops it. At that instant, how much time would Tara's timer say has passed? Using this equation, you get the answer that t equals 100 seconds. When Tanya is in a reference frame, moving at 0.8 times the speed of light relative to Tara's reference frame, Tanya observes that 60 seconds has passed, while Tara will observe that 100 seconds have passed. This means that time dilation has occurred. To further clarify time dilation, time is relative. This means that it's not absolute and will differ for an observer depending on how you are moving through space-time. If both you and the observer had synchronized working clocks, your clock would literally change in time and be slower than the observer's if you were moving at relativistic speeds. As you would compare the clocks, you will notice that they would be different in time from one another. Objects moving at relativistic speeds will also experience a length contraction, and the effects are relative to an observer, similar to how time dilation due to velocity works. An object moving close to the speed of light will be significantly and noticeably contracted in its length and will appear strange to an observer. The formula for this phenomenon is also derived from the Lorentz factor and very similar to that of time dilation. This online calculator can be used to calculate the value of length contraction depending on different variables. Another question special relativity poses is why the speed of light is unreachable and the maximum speed for anything in the universe. Why is the maximum speed something with mass can travel below the speed of light? The reason why is because objects with mass require energy to be accelerated, and once the speed of an object approaches the speed of light, the object becomes heavier and heavier to the point where it becomes so heavy it becomes impossible to make it travel faster. Momentum in special relativity is described using the Lorentz factor multiplied by mass times velocity. And as we increase the speed to relativistic speeds, the momentum will increase. This means that a greater force is needed to further increase speed. The momentum at the speed of light will be infinite and will require an infinite amount of energy, which makes it impossible to achieve the speed of light. Also, the relativistic mass of the object will reach infinity, thus also requiring an infinite amount of energy to reach the speed of light. If it were possible, the time dilation of an object traveling at the speed of light would become infinite, which means that time would completely stop, and the speed would also stop, which concludes that nothing can travel faster or at the speed of light. This graph shows the energy required to reach the speed of light, and as you can see, the graph is exponential and increases vastly once reaching speeds close to the speed of light. Since special relativity time dilation is only applicable in phenomena that isn't affected by gravity, there exists another form of time dilation described by the theory of general relativity. This form of time dilation is dependent on gravity, which is the opposite of special relativity time dilation, and is called gravitational time dilation. To understand this better, you need a good understanding of what gravity is and how it works. Gravity is an invisible force that pulls objects towards each other, and it is the force that draws objects toward the center of a planet or any other body. Earth's gravity is what keeps you on the ground and makes things fall. Gravity pulls objects together, but also its strength weakens with distance, so the closer the objects are together, the stronger their gravitational pull is. Isaac Newton figured out the gravitational constant of the universe, which describes the constant gravitational forces between two bodies. Einstein also used this constant in his theory of relativity to explain how gravity and the universe works. Anything that contains mass has gravity, and objects with more mass have more gravity. Gravity is also the force that holds the planets in orbit around the sun and what keeps the moon in orbit around the Earth. Earth's gravity, from its mass, makes a combined gravitational pull on all the mass in your body, which gives you your weight. If you were situated in a planet with less mass than Earth, you would weigh less due to a weaker gravitational field. You exert the same amount of gravitational force on Earth that it does to you, but due to the vast mass difference between you and the Earth, your force doesn't really affect the planet. For example, if you weighed 50 kilograms on Earth, on the Sun you would weigh approximately 1354 kilograms, due to the Sun's gravitational field being much stronger than Earth's, thus making you weigh more. As Einstein modeled space and time together in his theory of general relativity, he reasoned that any object with mass would interact with the fabric of spacetime and cause distortions. He suggested that gravity will lead to a distortion of spacetime. GR describes gravity not just as a force, but as a geometry. It's the consequence of how matter warps spacetime. Unlike other popular theories at the time, general relativity correctly describes the changing orbit of Mercury by taking into account the disturbances and distortions of spacetime caused by the sun's mass. Empty spacetime is completely flat, and it looks exactly like spacetime described in special relativity, but in our universe this is not the case. Spacetime in the presence of masses is curved, and in curved spacetime there are no straight lines. According to general relativity, gravity is a distortion of four-dimensional spacetime, or simply put, gravity is the curvature of spacetime. An object with large mass will have more gravity, thus having a larger distortion in spacetime, and vice versa. For example, if a bowling ball is placed in the middle of a trampoline, it will stretch the fabric and cause it to sag. A marble moving along the trampoline will naturally be drawn towards the ball in the middle. The warping of spacetime results in the geodetic effect, or the curvature of spacetime. Planets orbiting the Sun are not being pulled by the Sun, but instead they are following the curved spacetime deformation caused by the Sun, causing them to be attracted towards each other. The reason the planets never fall into the Sun is due to the speed they maintain and are traveling at. Matter distorts spacetime, and it is this distorted spacetime that affects other matter. Objects and planets such as Earth orbit freely under their own inertia through warped spacetime, following the shortest possible curved paths, known as geodesic paths, in the warped spacetime. Inertia is a natural tendency of an object to resist changes in their state of motion. A body at rest tends to stay at rest, and once set in motion, a body tends to stay moving at a constant speed in a straight line or along a geodesic path, unless acted by an outside force. The curvature of spacetime is dependent on the matter, energy, and stresses present within it. The contents of the universe define its spacetime curvature. A gravity well represents this distortion and curvature in spacetime caused by matter. It is a representation of the gravitational pull that a large body in space exerts. Anything on the surface of a planet or moon is considered to be at the bottom of its gravity well, where the gravitational field is the strongest. The larger the body, the more mass, thus the deeper the gravity well or curvature in spacetime will be. For example, the Sun has a large or deep gravity well due to its mass, while asteroids and small moons have much shallower or smaller gravity wells. More specifically, a gravity well represents the gravitational potential energy of an object in space. Gravitational potential energy is energy that an object possesses due to its position in a gravitational field. The most common use of this energy is for an object on Earth's surface where gravitational acceleration is at a constant of 9.8 meters per second squared. Objects with larger gravity wells possess more gravitational potential energy, thus requiring more force to counteract the gravitational forces. Since deeper gravity wells indicate more gravitational potential energy, more force is required to counteract the forces of gravity. Work in our lives is constantly done against our gravitational force, for example when climbing up stairs. Climbing out of a gravity well of a planet is easier and requires less force if the celestial body has lower mass and a shallower gravity well. Escape velocity is a minimum velocity an object must have in order to escape the gravitational field of a planet without falling back. The object must have greater energy than its gravitational potential energy to escape a planet's gravity well. For example, a spacecraft leaving Earth needs to be traveling at 7 miles per second or nearly 25,000 miles per hour to leave Earth's gravitational field without falling back to the surface or into orbit. Escaping Earth's gravity well is the most difficult part of space travel since so much energy is required to escape it, and also the weight of the spacecraft has to be accounted for. The gravity wells are the reason why it's easier and requires less energy to come back to Earth from the Moon than going from the Earth to the Moon. The Moon has less gravity than Earth due to its mass difference, thus having a less significant distortion in space-time and smaller gravity well, hence why escaping the Moon's gravity well and reaching the Moon's escape velocity is much easier than Earth's. As previously mentioned, counteracting the Sun's gravitational force and escaping its gravity well would be much more difficult than on Earth due to this very reason. The main takeaway from this is that matter or gravity warps space-time, so that space-time itself is curved. Gravity doesn't just warp space, it also affects time. According to general relativity, gravitational time dilation is a difference of elapsed time between two events as measured by observers situated in different gravitational masses in regions with different gravitational potential. Gravitational potential energy is lower when the observer is closer to the source of gravitation, for example closer to Earth's surface, which means that time will move slower for them relative to an observer in a higher gravitational potential energy location or further away from the gravitation source. Clocks will run more slowly in stronger gravitational fields. Massive bodies that have strong gravitational fields bend spacetime and cause deeper gravity wells, which was previously discussed, where time will dilate more due to the strong force of gravity caused by the body, which is represented in its gravity well. Objects such as the Sun that cause large gravity wells due to their mass will also dilate time much more significantly than objects with lower mass and a lower gravitational field, for example on Earth. The closer you get to the source of gravity or deeper into the gravity well, the stronger the pull of gravity will be, and the slower time moves relative to another observer. This means that time will be slower at the surface of Earth, where the pull of gravity is stronger relative to a frame of reference vertically situated above the surface of Earth. This effect is very minuscule and basically unnoticeable, but in areas with very strong gravity, the effects of time dilation is apparent and can be noticed, such as in a black hole. Since the closer you are to a massive body, the slower time runs, thus time runs slower for someone on the surface of the Earth compared to someone in orbit around Earth, since the gravitational pull of Earth is weaker in orbit compared to the surface. And this time dilation means that the apparent flow of time relative to another observer is affected by gravity. The flow of time is actually not changing for you depending on where you are. It will still feel like the same time for you and the observer, but it will be different upon comparison with the observer. The relative nature of gravitational time dilation is identical to that of the special relativity time dilation. Both are relative depending on where you are and where the observer is situated in spacetime. The equation for gravitational time dilation is T equals T0 multiplied by square root of 1 minus 2gm over rc squared. T0 is the change in time in a reference frame from an infinite distance from any mass, and this is the observer time, not in a gravitationally influenced frame of reference. Change in time in the gravitationally influenced reference frame is labeled by T. Variable c is the speed of light, variable g is the gravitational constant, variable m is the mass of the object being approached, and variable r is the distance from the object being approached. Gravitational redshift is closely associated with gravitational time dilation due to their connectedness. Gravitational redshift is the reddening of light due to the changes in its wavelength and frequency as it escapes from a gravitational well in spacetime. Einstein's theory of general relativity predicts that the wavelength of electromagnetic radiation will lengthen as it climbs out of a gravitational well. Since light is on the electromagnetic radiation spectrum, This occurs with light. Particles of light, known as photons, must expend energy in order to escape a gravity well, similar to previously discussed escape velocities, but at the same time the photons must always travel at the same speed of light. This means that the energy must be lost through a change of frequency rather than a change of speed. If the energy of the photon decreases, the frequency also decreases. This implies an increase in the wavelength of the photon or a shift to the red end of the electromagnetic spectrum, hence the name gravitational redshift. The opposite is also true, as the observed wavelength of a photon falling into a gravitational well will be shortened or gravitational blue shifted as it gains energy, which is also supported by the visible spectrum on the EM radiation spectrum. Gravitational redshift directly implies gravitational time dilation. Clocks in gravitational fields run slower than clocks in free space. Extremely accurate atomic clocks use the frequency of an atom's spectral lines, and 1 second is defined as this many periods, with our radiation corresponding to the transition between the two energy levels of the cesium-133 atom. Since gravitational redshift assumes that light is redshifted due to a gravitational field, it also means that time moves slower in the gravitational field that has redshifted light in it relative to another observer, hence implying gravitational time dilation. To summarize the reason why light is redshifted, it's because of a gravitational field being present when light is trying to escape, and this is similar with time. The frequency of a clock ticking on Earth, for example, will appear to an observer not situated in a strong gravitational field to be slightly lower than those from their clock. This means that the clock's tick frequency on Earth is moving slower relative to an observer not in a strong gravitational field, hence the slower time would pass relative to that distant observer. In 2014, 2 satellites of the Galileo European Global Navigation Satellite System were unintentionally launched on elliptical orbits around the Earth rather than the intended circular orbits. The elliptical orbits caused problems for their use in the global navigation system, but scientists turned this mistake into an opportunity. 2 teams used highly precise atomic clocks on the satellites to perform the most precise tests to date on gravitational redshift. Since clocks tick slower in a stronger gravitational field relative to another observer, time on the surface of Earth will be slower than in the atmosphere or anywhere above the surface of Earth, since the gravitational field will be weaker there. Researchers exploited the elliptical orbits of the satellites to test this with very precise results. Since the satellite in the elliptical orbits moves from the perigee to the apogee, or from the lowest point to the highest point and then back, oscillating between them both. This means that there is a large constant change in gravitational potential between both points in the orbit, more specifically from approximately 17,000 to 26,000 kilometers. According to Relativity, the atomic clocks on board the satellites will tick slower when they're closer to Earth and then faster when they're at the highest point. The satellites measured the deviation of gravitational redshift from the prediction of general relativity, improving the best previous gravitational redshift tests in over 40 years by a factor of 5.6. This experiment gives further proof and data to Einstein's theory of relativity on gravitational redshift and gravitational time dilation. Black holes in space affect time very severely due to their strange nature and strong gravitational influence. Black holes are a phenomenon predicted by Einstein's theory of general relativity. Even though his own theory predicted them, he strongly resisted the idea and did not believe in the existence of black holes. The general consensus currently is that black holes do exist and that they are actually one of the most important features in our universe. They have been detected indirectly in enough different ways that there is little doubt of their existence. A black hole is a region of space in which the gravitational field is so powerful that nothing, including light, can escape its pull, hence the name. Since nothing in the universe can travel faster than light, nothing can escape a black hole. A black hole is not empty space, but rather a place where an enormous amount of matter is squeezed into a tiny area called a singularity. Since black holes have such a large gravitational field, they produce extremely deep gravity wells in space-time. Einstein predicted that supermassive black holes can have masses equal to billions of suns and are likely to be at the centers of most galaxies. No matter the starting size of a black hole, they can grow throughout their existence, consuming anything that is close to them. The most common way a black hole is formed is by stellar deaths, or the death of stars. In the final stages of an enormous star's life, it causes a massive explosion known as a supernova. This explosion flings star matter into space and leaves behind its stellar core. While the star was alive, nuclear fusion created a constant push that balanced the inward pull of gravity from the star's own mass, keeping it stable. After a supernova, these forces that oppose that gravity no longer exist, so the star's core begins to collapse in on itself. If its mass collapses into an infinitely small point, a hole in space-time, a black hole is formed. Compacting all that mass, several times the mass of our sun, into such a small point gives the black holes its extremely powerful gravitational field. People cannot directly observe a black hole since the gravitational field pulls all the light into the middle of the black hole and would appear completely empty. Scientists can instead infer the presence of a black hole and study them by detecting their effect on nearby matter. If you approach a black hole, it would literally look like a hole of total darkness and blackness silhouetted against the background of space, with the light around it being distorted. More on that later. All possible bright stars and lights in the backdrop of space would be around the black hole, and it would appear as there is nothing there since the hole is completely black with no light passing through it. A black hole is bounded by a well-defined surface or edge known as the event horizon, within nothing can be seen or escape. Since the point where light cannot escape is also at that event horizon, it implies that nothing in the universe can escape that point either. This is because the speed of light is the absolute fastest thing anything can travel in the universe, and reaching that speed would require infinite energy. The event horizon of a black hole acts as a one-way membrane, or the point of no return. Within the event horizon, space itself is falling into a black hole at a notional speed greater than the speed of light, a distortion or hole in space-time itself. The definition of notional is existing as or based on a suggestion, estimate, or theory, not existing in reality. The black hole isn't actually breaking the constant speed of light in the universe and isn't going faster than the speed of light, but it appears this way due to the immense gravity. At the center of a black hole, there is a gravitational singularity, which is a one-dimensional point which contains a huge mass in an infinitely small space, in which density and gravity become infinite and space-time curves infinitely as well. This is where the laws of physics cease to operate successfully. American physicist Kip Thorne describes it as the point where all laws of physics break down. The most notable theories suggest that objects that fall into a black hole and approach the singularity at the center will become stretched out or spaghettified due to the increasing difference in gravitational attraction on different parts of the hole, but what happens once approaching the singularity is unclear and unknown. Certain materials in space, such as gas, dust, and other stellar debris, come close to falling into a black hole but don't quite fall in. They form a flattened band of spinning matter around the event horizon called the accretion disk. Although nobody has actually seen a black hole or its event horizon, this accretion disk can be seen because the spinning particles are accelerated to such large speeds due to the black hole's gravitational field, and due to this release heat and powerful X-rays and gamma rays out into the universe, which can be seen. Non-rotating black hole would be precisely spherical. However, a rotating black hole for a rotating star would bulge out at its equator due to centripetal forces. A non-rotating black hole is also known as a Schwarzschild black hole, after the German physicist Karl Schwarzschild. The core of this black hole doesn't rotate, and it only has a singularity and an event horizon. A Kerr black hole is a rotating black hole, which are more common in the universe. The core of this black hole keeps rotating due to conservation of angular momentum. Even though we cannot see a black hole, its mass and rate of rotation can be measured. A Kerr black hole has an ergosphere, which is a region outside the event horizon where gravitational forces start to influence the movements of objects. Objects in the ergosphere can no longer stay stationary in space, and depending on the distance from the event horizon, the gravitational force can be very strong or weak. If an object passes into the ergosphere of a rotating black hole, it can still escape from the black hole by gaining energy from its rotation. This is also a point where light can usually escape, being pulled into the event horizon. Spaghettification is the term for dying in a black hole. As you fall into a black hole, your feet begin to accelerate much faster than your head, and due to the difference in gravitational force in different parts of the black hole, your body would stretch out and become more severe to the point of guaranteed death. Astronomers call this spaghettification because the intense gravitational field would horizontally compress and vertically stretch you into a long thin shape, similar to spaghetti. In most black holes, the gravitational field is so strong that no object can withstand it, no matter how strong its components are. Karl Schwarzschild correctly found the relationship between the size of a black hole and its mass in 1916. Schwarzschild showed that any mass could become a black hole if that mass was compressed into a sufficiently small sphere, like a singularity with radius r, which is known as the Schwarzschild radius. Theoretically, anything with mass, for example a tennis ball, could be turned into a black hole if it was compressed into a small enough sphere. The size of this sphere can be calculated using the Schwarzschild equation, which gives the radius of the supposed sphere. The Schwarzschild radius is also the radius of the event horizon of a non-rotating black hole. To summarize, any object with a physical radius smaller than its Schwarzschild radius will become a black hole. The Schwarzschild equation is Rs equals 2gm over c squared. Variable Rs is the Schwarzschild radius, g is the gravitational constant, m is the mass of the object, and c is the speed of light. You can use this equation on Earth to find its Schwarzschild radius. These are the values for the gravitational constant, speed of light, and the mass of Earth. You can apply these in the formula to get this result. Rs equals 0.0088. This means that the Schwarzschild radius of the Earth is approximately 0.0088 meters or 8.8 millimeters. If you were to compress the entire Earth into this size or smaller, it would become a black hole. The light around a black hole visibly bends and is distorted. This is caused by a phenomenon predicted by general relativity called gravitational lensing, which describes that mass bends light. Any mass has a gravitational pull, which means that the gravitational field of an object with mass bends light. The gravitational field of a massive object will extend far into space and will cause light rays passing close by the object and through its gravitational field to be bent and refocused somewhere else in space-time. The more massive the object, the stronger its gravitational field, and the greater the bending of light rays around it. Gravitational lensing happens on all scales in the universe. Even the masses of our bodies will slightly bend light, but the effect is too small to be noticeable. The gravitational field of an object pulls most strongly in nearby space. For example, when light rays from a more distant object pass by, they are caught up in the gravitational field, thus bent and refocused. The refocused image is usually a distorted view of distant objects. Light coming from distant galaxies that pass close to a cluster may appear to be distorted or lensed by its mass and gravitational field. The effects of this can be very strong as the images of lensed galaxies are stretched and pulled into arcs as the light passes close to the foreground of the cluster. This image is a photo of the Able 2218 cluster, where the light has been clearly lensed by gravitational forces. The real shape of these galaxies are not this shape. Instead, they are usually elliptical or spiral shapes, but they appear this way due to the lensing of light. This shape distortion from lensing comes from the fact that galaxies are massive objects, and that light rays leaving from one side of the galaxy will pass through a different part of space on the other side. The light rays will therefore pass through different parts of objects' gravitational fields and will be bent in different ways. The effect of this is a distortion to the shape of the image of the galaxy. Black holes bend light very severely around it due to its extremely strong gravitational field, and the effects of gravitational lensing will be very noticeable. Light will be heavily distorted around the black hole, and the light coming from behind the black hole will be bent around it, leaving a large space of darkness corresponding to the black hole's event horizon. Unlike other objects we are used to, where they appear to get visually larger proportional to the distance you are away from them, black holes appear to grow much more quickly than you are expecting due to the incredible curvature of space-time caused by it. The apparent area of the black hole appears to grow dramatically as you get closer. When you fall into a black hole or get very close to its event horizon, its size and scale appears much larger than its actual size. This image is an extremely realistic animated simulation of what falling into a black hole would look like. In the animation, you can clearly see how drastically and rapidly the black hole appears to get closer to the person falling into the hole. As the person falls beyond the event horizon, their view diminishes, because there is no conclusive evidence and general consensus of what happens after you fall into the event horizon and towards the singularity. This remains a mystery. Due to the extremely strong gravitational field that black holes have, gravitational time dilation is very apparent. As you get closer to the black hole and towards its gravity well, time slows down relative to another observer. Near the black hole, the time dilation effect would be very extreme. From the viewpoint of an observer outside the black hole, time stops at the edge of the black hole or at its event horizon. For example, an object falling into the hole would appear frozen in time at the event horizon of the hole. If you were falling into a black hole, an outside observer would see your approach to the hole become slower and slower until you reach the edge of the black hole, the event horizon. This is a point in space where nothing can go back and light can't escape, so to a person watching you enter the black hole, that would be the end of your journey. It would be impossible for them to observe you falling into the black hole further than the event horizon due to its properties. You would seem almost frozen in time and space until the light coming off your body becomes increasingly redshifted until you fade into nothingness. The light of your body would escape the black hole since it wouldn't be past the event horizon yet, and due to the strong gravitational field of the black hole, the light escaping off of your body would increase in wavelength and become redshifted. To a person falling in the black hole, their perspective of time would stay the same due to relativity, and they would be spaghettified when going beyond the event horizon. Wormholes are theoretical solutions to Einstein's theory of general relativity that would allow time travel. In 1916, Austrian physicist Ludwig Flamm noticed that another solution was possible for the Schwarzschild black hole equation, which described the phenomenon that came to be known as a white hole. A white hole is a theoretical time reversal of a black hole. While a black hole acts as a vacuum drawing in any mass that crosses the event horizon, a white hole acts as a source that ejects matter from its event horizon. Some speculate that there is a white hole at the other side of a black hole, where all the matter collected by the black hole is blown out in some alternate universe. These two phenomena connect as wormholes, which is a hypothetical tunnel through spacetime that connects distant regions, thus providing a sort of shortcut through spacetime. Although there is no observational evidence of wormholes, they are valid solutions under the theory of general relativity. Just like the color black is the opposite of white, a white hole will be completely white instead of black, since light cannot enter a white hole, making it extremely bright. An Einstein-Rosen bridge is a wormhole geometry of a black hole and a white hole with two separate universes connected at their event horizons, connecting to make a shortcut through spacetime. If these bridges were possible, they would unfortunately be highly unstable, and it would be nearly impossible to pass through one either way due to a number of phenomena such as spaghettification in a black hole. Because wormholes are shortcuts through four-dimensional spacetime and not just space, Stephen Hawking and many others have proposed that wormholes might theoretically be utilized to travel through time as well as through space. Although this might be theoretically possible, it is widely believed that time travel into the past will never be possible due to a possibility of several paradoxes and self-destructive loops. Technically, wormholes would allow for travel faster than the speed of light, but not in a way that breaks any laws of physics. Instead, wormholes take advantage of the inherent geometry of spacetime by connecting two distant points in spacetime and connecting them through a wormhole. Going through a wormhole from point A to point B would be significantly faster than the speed of light traveling from point A to point B without the usage of a wormhole. This can be physically visualized by a piece of paper. Draw two distant dots on the paper and fold the paper so that the dots are next to each other, and the paper forms a curve. You can then visualize the change in distance between the 2 points on that piece of paper if a wormhole is used. This simple type of wormhole immediately collapses and disappears before anything can get through due to its gravity. Another type of wormhole is the traversable wormhole, which is a wormhole that can be crossed in both directions, which could potentially allow instantaneous long distance and time travel. This type of wormhole could theoretically be stabilized with exotic matter that would counteract its tendency to collapse. This form of matter would possess negative energy density, which would deflect radiation and repulse spacetime apart from itself. Instead of normal matter with positive energy density attracting objects in space together due to their gravity and curvature of spacetime, exotic matter would repulse or push away such objects. This matter would counteract the forces of gravity and would stabilize the collapse of a wormhole. This form of matter is purely theoretical and hasn't been proved to exist yet. Another way of traveling through the universe at a greater notional speed than light would be to use an Alcubierre drive. The Alcubierre drive, also known as the warp drive, is a theoretical idea based on the mathematical solution of Einstein's field equations that describe spacetime in general relativity. The idea was first proposed by Mexican theoretical physicist Miguel Alcubierre. An Alcubierre drive would allow apparent faster than light travel, but wouldn't break any laws of physics in the process, including the light speed limit. Instead, the Alcubierre drive would manipulate and exploit spacetime itself to move a starship or object. The concept involves the stretching of the fabric of spacetime in a way that would in theory cause the space ahead to contract while the space behind it would expand. An object inside this wave would then be able to ride inside this region, known as a warp bubble of space. This technology will not actually propel the spaceship into speeds exceeding light, but instead uses the deformation of spacetime permitted by general relativity to warp the universe around the vessel. The spacetime behind expands while the front contracts, and the path taken becomes a propulsion system manipulating spacetime. The spaceship or object would be pushed away from Earth and pulled towards a distant star by spacetime itself. The ship can ride the warp bubble to accelerate to high speeds and forward time travel due to time dilation. There are still many problems with this theory, for example the fact that the theory relies on the existence of exotic matter with negative mass and negative energy density so that it doesn't collapse under its own weight. Secondly, there aren't any known methods to create such a warp bubble in a region of space that will not already contain one, and assuming creating one is possible, there is not a known way of leaving once inside it. As a result, the physical usage of an Alcubierre drive remains hypothetical and theoretical. Another theoretical solution to Einstein's field equations in general relativity is a closed time-like curve. In a closed time-like curve, the world line of an object through space follows a path where it eventually returns to the same exact coordinates in space and time that it was in initially. A closed time-like curve like this could possibly be used to travel back in time. An extremely powerful gravitational field, such as a spinning black hole, could warp spacetime so that it bends back on itself, creating a closed time-like curve or loop that could be used to traverse back in time. The resulting time loop would be traversable. Imagine you're traveling along the loop. That means at some point, you'd end up at a moment in your past and begin experiencing the same moments all over again. Although this is a possibility, there is no known way of constructing such a phenomenon. Through all these possible phenomena, time travel could be achievable, but many believe that it isn't due to many paradoxes. Probably the most famous paradox associated with the possibility of backwards time travel is the grandfather paradox. The paradox is that you travel backwards through time and kill your grandfather before he met your grandmother, hence preventing your parents' birth and your own birth from ever existing in that universe. This means that you wouldn't have been born to be able to go back in time and kill your grandfather, but if you didn't exist to kill your grandfather, then you couldn't have killed him. Since you didn't kill him, you would be alive, but now you can go back in time to kill him again. This creates an endless loop and a paradox of backwards time travel that cannot be ignored. This is also why many scientists, such as Stephen Hawking, dismiss the possibility of backwards time travel. Due to this reason, time travel is difficult to the past, and there are many known ways of achieving it yet. For example, a basic wormhole hasn't even been proven to exist yet. Theoretically, the correct manipulation of space-time geometry might possibly allow time travel to the past under the right circumstances. Forwards time travel, however, is achievable and has technically been proven. Relative velocity allows time travel to the future relative to an observer not moving at relativistic speeds, and a gravitational field relative to an observer not present in a gravitational field also allows time travel. Both SR and GR time dilation allow apparent time travel. For example, if you traveled in a spaceship at extremely high speeds for 5 years and then came back to Earth, the time on Earth could be 20 years more than what you experienced, thus allowing forward time travel. Another logical proof that time travel to the past doesn't exist is that there have been no actual reports or accounts of time travels in our world. If time travel to the past is possible in the future, it would mean that our time currently would be accessible to them, so time travelers would probably visit our time period. There would at least be some kind of record or images of time travelers in the past from the future, but there aren't any. In 2009, Stephen Hawking threw a party at Cambridge University and everyone was invited but no one showed up. Hawking expected this as he only sent out the invitations after his party had concluded. He said it was a welcome reception for future time travelers as an experiment to reinforce his conjecture that time travel into the past is effectively impossible.